Okay, now I'm very glad to introduce our last speaker, Himanshu Khanchandani from Princeton University, who will tell us about CFT in AdS and Gross-Neveu boundary CFT. Please, Himanshu.
Thank you for the introduction and thank you for the opportunity to speak here. It's great to be here in London. I'm going to be talking about this paper that appeared last year with my advisor, Simone Giombi, and this other paper that appeared last month with Simone and Elizabeth. Okay, so here's the plan of the talk. I will start with some introduction and I will introduce the basic idea with the example of a free scalar theory. Then I will talk about Gross-Neveu theory in AdS, both the large N Gross-Neveu model and the description near 4 dimensions given in terms of Gross-Neveu Yukawa model. And then I will describe the corresponding boundary conformal field theory. And then I will end with some conclusions. Okay, so let's get started. The main idea is that a boundary conformal field theory has this, so Euclidean conformal field theory has symmetric group SOD plus 1, 1. And if you introduce a boundary, then the symmetric group breaks to SOD, 1. And this is also the same as the isometric group of ADSD. So you can study a CFT in Euclidean AdS, and that has the same symmetric group as the boundary conformal field theory. And this is also, if you write down the AdS metric in point care coordinates, this file scaling is pretty obvious. So, so what you do is you study your CFT in AdS, then the AdS has a boundary, and the boundary conformal field theory is the boundary of the CFT is on the boundary of AdS. And then, for instance, you can use the techniques from AdS CFT literature to calculate things about BCFT. So for instance, if you wanted to compute the 4-point function of boundary operators, you could do it by calculating Witten diagrams in AdS. Normally, you would have to calculate Feynman diagrams in half space, but there are a lot more techniques to deal with Witten diagrams in AdS than to deal with Feynman diagrams in half space. So this is what we'll be using. So let's start with the the simple example of a free scalar. If you start with a free scalar on half space, then this is the action of a free scalar on half space. And if you just do the usual variational argument, you would get this equation of motion with two possible boundary conditions. You can either have Neumann or Dirichlet. These are the two conformal invariant boundary conditions. And in Neumann boundary condition, you impose this. So the leading you impose a boundary condition, and then the leading operator on the boundary is just the phi like taken to the boundary, and it has dimension d over 2 minus 1. And if you impose the Dirichlet boundary condition, then the leading operator on the boundary is the derivative of field or the boundary, and it has dimension d over 2. Now let's see how this comes about from AdS. So if you study a free scalar on AdS, then this is the action for a free scalar on AdS, and then you solve the equation of motion, and you get the solution which has this behavior near the boundary, and this delta is related to the dimensions like so, and there are two possible values of delta, which are exactly d over 2 and d over 2 minus 1, and this is as I showed in the previous slide. These are the two possible dimensions of the boundary operators for a free scalar. This already said that. Then you can also see that the correlation functions are also related. So on flat half space for Neumann and Dirichlet boundary condition, you have the correlation function is just given by the usual 2-point function plus the image term just by the method of images. And in AdS, though, the 2-point function of a scalar is given by the bulk-to-bulk propagator, which has this expression in terms of 2f1. But if you plug in the value of delta to d over 2 or d over 2 minus 1 for Neumann or Dirichlet boundary condition, you will get exactly this 2-point function. So one thing to note is that the bulk-to-bulk AdS, the bulk-to-bulk propagator in AdS is also the same as so a 2-point function in a BCFT can be expanded in boundary channel conformal blocks, as was also pointed out in the previous talk. Then the boundary channel conformal blocks are exactly the same as bulk-to-bulk propagator in AdS. This is just a statement about kinematics, though. Okay, so now next thing I will study is the Gross-Neveu model in AdS. So to start, let's consider the free massive fermion in AdS. So a fermion in AdS can have two possible boundary conditions. You can act gamma 0, and you can get the fermion itself or minus the fermion. And these two choices correspond to a boundary fermion operator of dimension d minus 1 over 2 minus m or plus m. Here I'm assuming m is positive. So this is all that happens for the free fermion. So we can then consider the Gross-Neveu model in AdS. Gross-Neveu model has n fermions and Hubbard-Stratonovich scalar sigma, and there is this this 3-point coupling between the two. So we can integrate out the fermions and get this effective action in terms of sigma. Since the fermion appear quadratically, we can do that. And then at large n, we can do a path integral over sigma by assuming a constant saddle point for sigma. So now in flat space, the saddle point would just be sigma equals 0, and that would be the solution at large n. But in AdS or in half space, there could be non-trivial value of sigma. The advantage of being in AdS is that in flat half space, the 1-point function of sigma operator would be just 1 over the distance to the boundary. But in AdS, it's just sigma equals constant. So we can literally, we get this saddle point equation, which is just extremizing this effective action. And here we can just take sigma to be constant. So in practice, the effect of sigma at leading order in large n is just to act as a mass term for the fermions. So now we can solve the saddle point equation. But to compute this trace, I need to tell you what boundary condition to impose. And as I said before, for a massive fermion, there are 2 boundary conditions that one can impose. And so if you impose the minus boundary condition, then you compute the trace and you calculate the saddle point, and you find that the saddle point value is given by sigma star equals d over 2 minus 1, which gives you the boundary dimension to be d minus 3 over 2. And I'm going to call this phase B1. And then for the other choice of boundary condition, you can impose plus boundary condition, and you get a saddle point, but you only get a unitary saddle between dimensions 3 and 4. There is no unitary saddle for this boundary condition in less than 3 dimensions. And there you get this value of sigma star, and that gives you the boundary dimension equals d minus 5 over 2. And I'm going to call this phase B2. And this is all there is at leading order and large n. But we can go to subleading order n 1 over n. So to next order n 1 over n, we will have to expand the sigma around the saddle into fluctuations, and then calculate the effective action in terms of the fluctuations. And this is the quadratic piece in fluctuations. And to calculate the propagator of the 2-point function of sigma, say, I had to invert this kernel. Now, you can do that. You can do that for both the phases that I said before. But if you choose this phase, then there is a unique choice of sigma propagator that you find. But if you choose this value of sigma star equals 2 minus d over 2, the B2 phase, which exists only between 3 and 4, then you realize that there are 2 inverses of this kernel, and they correspond to 2 different phases on the boundary. In particular, the scalar sigma induces a boundary scalar, and those two in these 2 phases, there are 2 different values of the boundary dimension of sigma. So these 2 are 2 and d minus 3. And these 2 phases, I will call these phases B2 and B2 prime, and they can only be distinguished at subleading order in 1 over n. At leading order in 1 n, they are the same. So here is a picture of the phase diagram of this BCFT between dimensions 2 and 4. You have phase B1 and then B2 and B2 prime. And near 4 dimensions, as you can see, there are three possible phases. So I'm going to next describe quickly what are these phases in the Gross-Neveu model near 4 dimensions. The Gross-Neveu model has n fermions and a scalar s, but now the scalar is local. So now on the scalar, you can choose to impose either Neumann boundary condition or Dirichlet boundary condition, or you can give a classical wave to the scalar s, because you have on the AdS, you have this potential. You have this conformal coupling term, and you have this positive term in the potential. So you can minimize this potential to give a classical wave. And these 3 phases correspond exactly to the phases B1, B2, and B2 prime in the large n model. So when S has a wave, this phase corresponds to the B1 phase, and when S has no wave, you can either impose Neumann or Dirichlet boundary conditions, and these 2 cases correspond to B2 and B2 prime phase. Okay, I think I'm out of time, so I will stop here. And I will take questions. I'll conclude and take questions.
Well, I think you have half a minute more if you want.
Oh, okay, okay, thanks. I will just describe quickly in one line what I was going to say. So what I described so far in epsilon expansion was what happens at leading order in epsilon, but to go to like subleading order in epsilon, I had to compute between diagrams in AdS. So one example, say I wanted to compute this correlator of S to leading order in epsilon, I will have to compute these two diagrams in AdS. This diagram in particular involves two integrals over AdS, and this sounds hard. But we came up with an easier way to do it, which is the following. The scalar S actually has an equation of motion that it satisfies. So in the Gross-Neveu model, if I take this propagator and I act the equation of motion operator twice on it, then I get this. Then I get this equation of motion for the two-point function. And here on the right-hand side, I already have the factors of couplings in front of these two-point functions. So I can just plug in these correlators in the free theory, and that will give me information about the two-point function to leading order in epsilon. And surprisingly, we can actually solve this equation. So this is a fourth order equation in the cross ratio, and we can solve it, and we can exactly get the two-point function of scalar S as a function of the cross ratio. And this once we have this two-point function, this actually gives us all the BCFT data that we need to know. We can also, I will also mention in the end that we also did this for the fermion. So you can do this, you can use the same trick for the fermion, for the fermion two-point function. You can apply equations of motion and you can get the correlator exactly. So using this method, we fix both the fermion and the scalar correlator in Gross-Neveu model to leading order in epsilon.
Mm-hmm. Yes. Okay.
That's all I wanted to say.
Okay, thank you. Yeah, we are slightly out of time. So let's thanks as a speaker. And now it's the time for questions. Maybe just very small questions. So you mentioned non-unitary saddles. So it is saddle points which beyond the unitary bound.
Yeah. So below the unitary bound. Like
So there are other non-unitary saddles, and if yes, what you do with those?
So yes. Yes, so in general, for instance, this saddle that I described.
So in principle, if you do saddle point approximation, it's not surprised that you will have some strange saddles. Yes, I don't know, right. Complex, some complex in general case. So, but
yeah, here all I meant was that this dimension will go below unitarity bound for the fermion, for the boundary theory. So on the boundary theory, you have unitarity bound that delta has to be bigger than d minus 1, d minus 2. So for the fermion, say, you have a unitarity bound that delta has to be bigger than d minus 2 over 2. And then, well, this is, because the boundary theory has dimension d minus 1. And so this dimension will go below this unitarity bound in less than 3 dimensions. That's all I meant here.
Okay. So, but still, does it have any physical sense or not at all?
I mean, I think this is still physical, but it's just not unitary, I think.
But so that I'm okay.
Yeah.
So, any other questions? Okay, if not, I don't know, if you want, maybe you could, and if you want to add something, no? Okay.
Yes.
Okay, so then I think we can thanks the speaker again. Okay. And let's thanks all our speakers today. So for these excellent talks. And now we stop